Okay, resistance, resistors, and resistivity. Got that? Yeah? Okay. Right, a few things to do, a lot to do, a lot. Okay, so look. You know from the last lesson that charge Q equals IT. So you could divide and you could get current is the rate of change of charge per unit time. In other words, you could say I is Q over T. That's pretty straightforward. So don't think you need to write that down. The next one though, which is you do need to write down, is voltage. Now voltage is like potential energy, okay, per unit charge, and it's in joules per coulomb. So 1 volt means 1 joule of energy per 1 coulomb. So if this 1 coulomb can do 1 joule of work, we say it's 1 volt. Yeah? Okay, so you need to write that down. Oh, is that okay, Ming? Is it? Yeah? A little not okay? All right. You got that? Yeah? Okay, continue. Continue? Yeah? Okay. Resistance. So, resistance of an electrical conductor is a measure of the difficulty to pass an electric current through that conductor. The unit used is the ohm. When 1 ohm of resistance means 1 volt of electric energy was converted into another form of energy when 1 amp passes through it. So what does that mean? That means when you have 1 amp and you lose 1 volt, then you say that's a resistance of 1 ohm. So 1 amp. Remember, amp is coulomb per second, okay? So 1 amp means 1 coulomb per second. And remember what 1 volt means? It means 1 joule per coulomb. So if 1 coulomb loses 1 joule, then we say there was 1 ohm of resistance. Why might the coulomb lose its ability to do work? You know, if I have a coulomb and the coulomb moves from me to you, and when it gets to you, it's lost a joule. Why? Maybe it released heat. What else? Yeah. So how could it have lost it? Well, the first answer was maybe it lost it because of heat. Right? You know sometimes wires get hot. But another possibility is that before the Coulomb got to you, it did some work on the way. So maybe the Coulomb left me, went into my laptop, made the screen light up, and then went to you. You know? Resistance doesn't have to be a bad thing. It could be because something useful was done with the lost jewel. I know it's a bit difficult. Is it okay? Or? I know it's not, I'm afraid, sorry. It's a useful definition.
It is all the definition you remember?
For today?
Not for today, for the exam.
Oh no, there's more definitions.
Okay.
Yeah.
Good to remember. That's not.
Whew, you got that? Yeah? I see a lot of people writing still. Continue? Jason? Yep. Okay, so next one, potential difference, PD, is just another name for voltage. Yeah. What, Bello? What? Look, that's life. What? Yeah? Yeah. See, Ming's not complaining. It's basically the same thing. Can I continue? Yeah? Now, the following picture will help explain the relationship between voltage, current and resistance. Okay? So, the following diagram will help explain the relationship. It's internet memes. So, what's the resistance doing? It's making it more difficult for the current to pass through. The voltage is losing work. The voltage is wasting energy trying to push the current through. Yeah? Okay, well that's not good for the exam. So we'll get to the proper relationship later, but in my mind I picture it like this. Okay, so how can we measure voltage? Well, we measure voltage using something called a voltmeter. Pictured so. So I think it's enough if you just write down the name. Measure voltage with a voltmeter. Hmm? What? 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 If you can do what? If you want to. I don't know what the problem is. Bellow! I thought I can join in. No? Yeah. If you get to say Dammy, I get to say bellow. Yeah, okay. Right, continue. I need to practice. Bellow. Bellow. Practice. Right. Continue. Yep. How do you measure current? You measure current using an ammeter. Guess what the picture looks like? Ah, no, totally different. See, that measures voltage. Not measuring current.
Well, I really like digital devices now.
Say again?
I really like digital devices.
Yeah, I know, but I like these ones more.
Like the speaker that does it.
Ah, yeah, but these are classic.
Doesn't mean it's just
These are classics.
It's measuring it.
just shows you that light is.
Oh, that's not
That's measuring
That's
it.
measuring.
To tell you.
No, I wouldn't say that's measuring it. That's the detective. Yeah.
Teacher, do it with a slap to that. Teacher, do it with a slap to that.
The slotting.
Yes.
They felt the best.
Oh,
thing.
nice.
Who did measure the best?
Don't worry, we're testing us out of context.
Come on. So the two of you want to detect a slap. Right. How do we measure resistance? What do you think we use?
Resistor.
No. Oh, look here. How do we measure voltage? We use a voltmeter. What's the unit for voltage? The unit is volt. How do we measure current? Using an ammeter. What's the unit for current? Amps. How do we measure resistance? Using a ohm meter. Do you want to see what it looks like? Do you ready?
No,
There you go. Now, in fact, these are rarely used as they are inaccurate. Well, it's true, these machines are a bit outdated, but even just using a digital ohm meter is not so common. They're not very accurate. Okay, they're not very accurate. So on this course, we don't use this. We only study and use voltmeter and ammeter. Okay, can I continue? Yep. Now, we'll not study ohm meter.
But if it's not accurate, how do you...
That's an experiment. We can use a voltmeter and an ammeter together to measure resistance, yeah. That's actually one of the experiments. They're pretty good. Now, note, an ammeter requires current to flow through it and a voltmeter between 2 points. So I need to try and explain this with a wire. Oh, I can just unplug my cable here. Now, if you want, so let's pretend that this is the ammeter. Okay. If you want to measure current, all you do is you plug the wire in one side, and then plug another wire coming out, and then it just measures the current as it passes through. Okay. And you might think, oh, this is the same as how a voltmeter would work, but no, voltmeter is a little bit different. So you have a voltmeter, you have a wire like this, and the electrons are moving through it, and you have your voltmeter, and you don't put the voltmeter in here like this. Okay, what you do is you have two wires that come out of the voltmeter, and you take one wire and you clip it here, and you take one wire and you clip it here. And the voltmeter can tell you the voltage difference between these 2 points. Okay, so the difference is for the ammeter, you put the ammeter in the current, and the current goes through the ammeter. Okay, whereas the voltmeter, you put it outside. So if there's a voltage here, you clip 2 ends. Well, I wouldn't say you stop it, but you clip either side of the cable. Yeah?
So like every wire without a power source or anything already has current flowing through it.
No. You'd have to connect this to a power supply. Yeah. I'm just trying to show you the difference. The ammeter sits inside of it, whereas the voltmeter sits outside, and then you connect it with 2 little wires. Okay? You get what I'm saying? Yeah. So ammeter goes inside the current, and then the voltmeter connects outside of it with 2 little wires attached. Is that okay? Yeah. Have you seen this before? Yeah. Okay. So this following picture is better for VIR. It's VIR triangle. So if you know 2 of these, you can get the third. So voltage is current multiply resistance. Resistance is voltage over current. And current is voltage over resistance. The VIR triangle. Draw that.
Yeah. VIR.
Yeah. Yeah. Continue? Continue? Yeah. Right, now we've more to do, but here's a quick, simple example. An ammeter measures 250 milliamps, and the voltage is 220. What is the resistance? So according to this formula, it's V over I. So what would that be? $880 ohms. Yeah? Okay, right. I don't think you need that one. So, all electrical devices, TV, PC, phones, they give resistance. But a resistor is a special electrical device that offers a fixed amount of resistance. It's used in experiments and circuits. Normally it releases a bit of heat. So here's a little picture of a resistor. These guys here are quite small. Their only job is simple. Just one job. When the current passes through, they give resistance. They make life difficult for the current. Yeah? So the current passes through and we lose some voltage. So for example, maybe we had 12 volts here and we pass through and it comes out as 10 volts. What was the voltage drop here? It's dropped to 2 volts. Okay? And if this is 1 amp, then what do we say the resistance is here? We say it's 2 ohms. Remember? We said 1 ohm means you lose a volt for every amp. Okay, so if this is 1 amp and it loses 2 volts, we say that this has a resistance of 2 ohms. These are called resistors. But what affects the resistance in a resistor? That is, what affects the calculation of the OR? Do you think the length affects it? So if I make this longer, would that be more or less resistance? What do you think?
More.
Yeah, I think it might. It'll make it more. Yes. Okay. What else might affect it? Material, the area. So how would the diameter affect it?
If it was smaller, bigger, like the resistance would be less, right? Diameter.
It's actually the opposite, believe it or not. If the area is bigger, you'd think that would mean more resistance. It actually means less resistance. Yeah, less resistance, yeah. It's true. Yes? Yeah, no. You said the type of material. That would affect it too. Okay. So you can put all these together and get this formula. The formula for the resistance is rho. Now this is not density. It's not density. It's a constant. Rho L. What do you think the L is? The length. And A. Area. S? You want to use S instead of A? Really? Is this what they do in China? Use S here. Big S. Big S. Oh, really?
I have the difference.
Oh, excuse me. Excuse me. He's international, but you're normal.
He's in international school. I am in normal school.
You see what she's saying?
Yeah, like.
She's normal and you're not normal. Yeah, no, look. I would like you to use A, please. Okay. This constant here has a name. We call it the resistivity constant. Yeah, it's different for each material. You got that? Yeah. Continue? Yeah? Okay. Resistivity measures how much an electrical conductor stops the flow of electricity through it. Most... Hello, what's wrong? What's happened? Oh. Okay. Most metals have a low resistivity. Oh, and the units, you could work it out, not too difficult. The units are the ohm meter. Okay, so if you can write this down too. No, you should really do this, I'm sorry. It's hard to draw, I know. Continue? Continue? No, I see some people writing. I see 4 people writing. What class did you have this morning?
Chemistry.
Chemistry. And what are you doing in chemistry? Reaction. Well, that's easy.
Well, easy for you, not
No.
for me.
No. I don't like chemistry. It's boring.
You like
So
math?
physics is interesting.
What?
So physics is interesting.
It sure is. Right, have you got that? Have you got that? Yeah. Right. Now, you don't need to write this. Don't need to write this down. Okay. Listen. You don't need to write this down. An insulator gives resistance. Not always, but usually has a high resistivity. And a conductor will not give resistance, and it usually has a low level of resistivity. And I can show you this with some values, okay? So the first one is carbon. Conductor or insulator? A conductor. You see, the resistivity is quite low. Yeah? Copper, conductor, 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 and now look, insulator. See the difference? An insulator. Okay. Now, I'll just tell you which value you need to write down, because you don't really need these. Yeah, just write down this one, nichrome. We'll need that for the example I have. Nickel and chromium, isn't it? No. I'm just giving you some examples. Can you just write down nichrome, please? Well, I call it nichrome, but I shouldn't really. I should call it what? Nichrome? Nichrome. Nichrome? Nichrome?
You added to another set of C.
I did, didn't I?
Nick.
It's like it was NICC.
Yeah.
Yeah. Nichrome. Yeah. That sounds weird. Nichrome? Nichrome? Huh? Well, it's just a mixture of the word nickel and chromium.
I see.
Huh? Who's the top in EAP here?
No, me.
David.
It's David.
David.
Yeah.
How would you say this?
I see what. Nico. Oh,
Yeah.
Nico.
Nichrome?
Yeah, Nico.
Yeah, okay. Okay, fine. What? What's going on?
That means
Don't you say Google?
that means wrong.
So you're just adding need to Google.
Hi, what's this? This is Nick Google Chrome. Right, okay.
It's Nichrome, I knew it.
Nichrome.
Yes.
Nichrome, that sounds like a Fast and Furious movie or something. Fast and Furious 8, the Nichrome. Right, let's have a look at this one. Very simple. An electrical heater is a piece of nichrome with a current through it. The nichrome is 200 centimeters long and 5 millimeters in diameter. How much resistance is there in the wire? So the formula is rho L over A. You know the rho, don't you? What's the L?
208.
2.
2.
And how do you get the A?
It's about 1.5.
Pi r squared.
About half.
But be careful, this 5 is the diameter. You need the radius. Calculate it for me, please.
Yeah, but like, the minute you change
Oh yeah, it's meters. You guess 10 to the minus 3 million. Got your calculator? This classroom is much better for walking around. Not like B or A401. Yeah, okay. Got an answer, Lee? Yeah, it could be. Seems pretty small, doesn't it? Yeah. Yeah. You got it, Marmont?
No, wait.
You got it, Eva? Yeah. You got it?
0.11. Yeah.
Huh?
0.11.
Correct, 0.11 ohms. So really this morning, I know lots and lots. What's wrong, Bello?
Maybe calculation error. I think that's
It's most very wrong, okay. Now, Jason, you got it? You got it? What did you get?
No, I just get it.
Okay, fine. Now, Marwan, David. So, today's two lessons have lots of definitions in them. Lots and lots and lots and lots and lots. But we only had 3 simple formulas. The first one was Q equals IT. Then we had the VI/OR triangle. And then lastly, we have this formula for calculating resistance in like a wire. You know? And actually, David, if I just go back here to the formula, you can see what I was saying to you a moment ago. Come on. There. Because the A is in the denominator, a bigger area makes for smaller resistance. A longer wire makes for more resistance, and a bigger constant, more resistance. Yeah? So if we look at the values here, which material has a lot of resistance in it? I think, what did I say, rubber, was it? Yeah. Now what's interesting is, you know, copper is very low, isn't it? I think copper's the lowest one here, isn't it? Yeah? Yeah, it is, isn't it? Yeah. But copper is not used, it is used, but the problem with, well, it's not even not the problem with copper. Copper has many advantages. It's soft, brittle, or not brittle, it's malleable. No, this is the problem. It's the opposite of cheap. Copper is expensive. It's expensive.
But the silver is more expensive than copper.
Of course. And gold is more expensive than silver or copper. Silver.
A silver can come down very fast again.
I know, but it's too expensive.
Yeah,
Too expensive. So, I mean, copper is used, but I mean, it's quite expensive. A lot of people steal the copper wire from construction sites. You know, because the construction company would get in a big wheel of copper wire. You know, it could be like, I don't know, kilometers of copper wire wrapped around. You know, so if you steal that and melt that down, we'll get you, I don't know, we'll get you a few hundred, maybe even 1,000 or 2.
Yeah, but use copper.
You're copper. Copper mines. Yeah, okay, so natural resource copper then. Okay. What they do when they're building highways, before the highways are open, when they put the street lights on, they turn the street lights on before the highways open. And my physics teacher was asking the construction workers, like, why are the lights on when the highway is closed and it's under construction? So they put the lights on to stop people ripping the copper wire out from the street lights. Because if the lights are on and they try to rip the copper out, they'll get electrocuted. You know? So copper's expensive, and people stealing it is a big problem. When I used to live in Dublin, the church I went to, they would have like copper, you know what I mean, like copper cups and copper crosses and things like this. And people would come in sometimes and steal these.
From church.
From church. They'd steal this to melt it down. Do you know? So
Really, I never hear people will steal the.
it's outrageous. It's outrageous. Do you know? Like imagine, you know, what? You know, I'm sure it's as outrageous if somebody went into a mosque and stole something, right? Imagine people going into the church and stealing the copper cross so they can melt it down. You know? So anyways, copper is a very good conductor, but the problem is it's very expensive. Okay? Now how are we doing for time? Okay, there's a couple of minutes left. Can you just try at least one of those now and you can finish them at home? Okay, so just give one of them a go and then you can go.